We'll move on now to one of my favorite mathematical subjects. This is the subject of probability theory, which is a way of trying to understand random processes. So what are we interested in here? We're interested in quantifying random events. So the kind of canonical example is, I flip a coin many times. Can I estimate the likelihood or probability that I get a certain number of heads or a certain number of tails? Or any sort of quantity that depends on this random outcome. So it is, from a mathematical standpoint, has a very rich and well-studied history. There are many sort of very difficult problems in this field, lots of kind of things that don't make a lot of sense until you think about them, and plenty of famous brain teasers. One of my famous is what's called the Monty Hall problem, which confounds very smart people to this day. I love this thing. So if you find this stuff at all interesting and inspiring, give yourself a chance to learn a little bit more and look at the Monty Hall problem. So the notation that we'll use is this kind of fancy blackboard P of A to refer to the probability that the event A happens. So an event is sort of any kind of outcome that depends in a random way on whatever you're talking about. So for example, if I flip a coin 2 times, one example of an event could be I get 2 heads. Another event could be I get 1 heads, 1 tails. Another event could be I get 2 tails. So these events should somehow depend on the random process you're studying. And just as a remark, it might make sense to talk about probabilities in terms of percentages. That is not what we are going to do. So percentages are out, numbers between 0 and 1. This is in. Okay. So for us, a probability of 0 means the event essentially cannot happen, and an event with probability 1 is essentially certain to happen. And then in between, there's some measure of likelihood. Okay, so a bit more notation. It's very interesting to talk about different events occurring simultaneously, or the probability of one event happening or another event happening. So let's give a little bit of notation for this that tends to feature prominently on at least the theoretical questions for the CLEP College Mathematics exam. So for 2 events A and B, we say that the union of A and B is the event that either A or B happens. So the union says I'm going to put A and B together, meaning I can either be in A or I can have B. So or means I've sort of expanded my possibilities, hence a union. Okay, so we use this upward-facing U here to denote this. Okay, so just to write it again, A union B is A or B. Well, if we're going to talk about or, we're going to also talk about and. So in order for this event to happen, I need both A and B to happen. Now this is more restrictive. This is more restrictive than either A or B. It was individually. So we call this the intersection of A and B, and it's denoted with A and upside down U. So A upside down, B is A and B. Okay? If I'm interested in the probability that some event does not happen, I want to give a name to the event. This thing does not happen. This is what's called the complement of an event. So the complement of A is the event that A does not happen. And it's denoted with A with a little subscript, or superscript C. So AC equals not A. So for example, if A is the event 2 heads, A complement is the event not 2 heads. Okay? it can be helpful for this to look at a Venn diagram. So I'll draw a little box here. So let's say I have the event A and the event B. Their overlap is the intersection, A intersect B. The part that includes either of them, this green part that I'm shading now, is A or B. So the U says I'm going to increase my event space. I'm going to say either I can be in A or B, which makes things bigger. And the upside down U is the intersection. This says I need to have both A and B happen. This is restrictive. This means I have to be in the middle of the Venn diagram. Now, and a couple important rules for probability theory are actually based on this notion of union and intersection. Okay, the most important one, and the one that tends to trip students up the most, I think, is this notion of union law. It says that if I want to compute the probability that A or B happens, I can do it in the following way. I can either have A happen, so I get the probability of A, or B can happen, but then it's not just enough to add the probability of A and the probability of B. I need to subtract the probability that both of them happen. That is, I need to subtract their intersection. Okay, and this is to avoid double counting. So the union rule is somehow the most, or the union law is somehow the simplest and most fundamental probability rule. But people always seem to forget to subtract the probability of A intersect B. So it's very common to be asked questions about, well, I'll ask you to find the probability that a union of things happen, that A or B happens. Don't forget to subtract the probability that they both happen. It's a very common mistake. We need to introduce some notions of what's called independent events. So we say that two events A and B are independent if the probability of A and B equals the probability of A times probability of B. This is somehow ideal. It would be very nice if all I had to do to compute the probability of an AND scenario was take the first thing's probability multiplied by the second thing's probability. This doesn't happen unless A and B are independent. So it's nice if people say, well, these two events are independent. Then it's much easier to compute their probabilities. If they're not independent, you have to be much more delicate with these things. So it's important to note how the independence condition could be used in the CLEP. They could tell you these events are independent and then ask you to compute things related to them. And you can use the fact that they're independent to use this trick about the probability of the intersection as the product of the individual probabilities. It's also possible they ask you something as simple as the following. They tell you probabilities of A, B, and their intersection, and they just ask, are they independent? Well, if they're independent, this must be satisfied. So it's a very simple question if you understand the concept, impossible if you don't. And what does independence sort of refer to at a kind of more basic level? That A has nothing to do with B. Right? That somehow they operate in completely separate spheres. Right? So, for example, two events that might not be considered independent would be the events, it's raining today and I'm wearing rain boots. If I know it's raining, the chance I'm going to wear rain boots is much higher, right? So these two events are somehow related. Events that are completely unrelated are the events that are what are called independent. Okay? We do need this other notion called conditional probability. So this P of A given B is how this is read. This is saying, assuming the event B is known to be true, that is, given the information of the event B, what's the probability of A occurring? So for example, if the event B is, it's 0 degrees outside, I could ask the question, what is the probability that I'm wearing a big coat given the fact that it's 0 degrees outside? Well, that probability is almost certainly higher than the probability that I'm wearing a big coat knowing nothing about what it is outside. This additional information, being given that it's very cold outside, tells you something about how to compute the probability. So that's the intuition behind this probability of A given B. Now, it has a very specific formula. Right? I can always compute the probability of A given B by computing the probability of A intersect B and then dividing by the probability of B. So it's important to know the formula, but it's also important to know the intuition behind conditional probabilities. And the last basic principle we wish to examine is simply the law of the complement, which is very compact. It says that the probability of the complement of an event happening is 1 minus the probability of the event happening. Another way of saying this is that the probability of A plus the probability of its complement is equal to 1. So how to interpret this intuitively? Well, this is saying that with certainty, either A happens or it doesn't happen. Right? The probability that A happens plus the probability A doesn't happen should be 1. Either A happens or it does not. So this almost gets to like a philosophical point. There are some mathematicians who essentially disagree with this, that there should be a third possibility, but it's very unintuitive and really only makes sense theoretically. But these are our basic principles, and we'll use these to study classic problems in probability in the next section.